Greetings, this is Matt Roscoe from the University of Montana with a lecture on powers and polynomials in our Math 171 calculus course. So today, let's just preview what we're going to do. I'm going to tell you we're going to get after some rules of differentiation. This is what Chapter 3 is all about: shortcuts to differentiation. And we start at the beginning with dealing, with kind of simple ideas about what simple rules should we have. And a lot of these rules will be kind of reviews from Chapter 2, where we were looking more conceptually at the derivative. So we'll find a rule for the derivative of a constant. We'll establish a rule for the power for power functions. We'll establish a rule when we have a constant multiple in front of a function. We'll establish a rule for sum and differences. And where this is kind of all heading, you can imagine if you got power functions that are being multiplied by constants and added together or subtracted, then what you got in these, I guess, 2, 3, and 4, well, as well as 1, are polynomials. So when we combine, all of these rules into, I guess, use, that should allow us basically to find the derivative of any polynomial. And then I have a few examples loaded. So off we go to the races. Let's do the derivative of a constant first. If c is a constant, then the d by dx of c is equal to 0, meaning the derivative with respect to x of a constant is equal to 0. So just kind of what we learned earlier in the course, and we kind of thought about a constant function and its slope. Well, a constant function is just a horizontal line. A horizontal line has slope 0. So we have a concept that this should be 0 from our last chapter, but in this chapter we're going to go after it a little bit more rigorously and actually prove these things to be true beyond a shadow of a doubt. So let's go ahead and switch over to my my Elmo cam here and see if we can get a sense of why this might be true. So let's see here. Pull this into screen. Oops, went the wrong place with it somehow. There we go. There it goes, large screen. Okay, I think we can see that all right. I think I'll work horizontally since it seems to work better in this particular screen. So what are we after? Let me get my notes over here so I don't make a mistake. So I'm after this idea that the derivative d by dx of a constant is equal to 0. So that's really my hypothesis. But we in mathematics are somewhat, I guess, nervous anytime we see a statement of something we're not certain about without some proof. So let's go ahead and prove it. Let's go ahead and let's let the function itself, f of x, be equal to the constant function. Then we can apply the definition of the derivative, right? We know then that d by dx of c is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So again, this idea of the limit of a difference quotient, that's how we find the derivative always. So let's go ahead and plug in to our constant function. So let's see, if I put x plus h into this constant function, what do I get? Let's just think about that for a second. X plus h plugged into a constant function, well, that's just a constant, right? F of x itself is just a constant, so we get c minus c all over h, right? Well, c minus c is just 0, so we get the limit as h goes to 0 of 0 over h, right? And 0 divided by anything is just 0, so the limit as h goes to 0 of 0. Just to convince yourself, just what you're asking is, division asks how many of these are in there. Well, I mean, in 0 there are none of these in there. So we get just the limit as h goes to 0 of 0, which of course, is going to be just equal to 0, and we've proved our statement. Okay, so there's the first, I guess, task done, right? Let's go ahead and go to a much more difficult task, and that's this one. It says if n is any real number, then d by dx of x to the n is equal to n times x raised to the n minus 1. So a little bit harder. This is the thing that we like to call the power rule, right? So our hypothesis here is that d by dx of x to the n is equal to n times x to the n minus 1. So let's go ahead and prove this for n a real positive integer, and then we'll talk about there was nothing in the hypothesis where n is n a real number. So if n is a real number, that means it could be something other than a whole number. But for our proof today, I'm going to do it for a whole number. It turns out that actually to prove it for all real numbers, we need some other differentiation artillery on board. So we'll come back to this and sort of plug up the holes that we're going to miss. But let's go ahead and start out by proving this. Let n be a positive integer. Okay. And let's go ahead and get started by applying so the derivative is always equal to the limit as h goes to 0 of the difference quotient f of x plus h minus f of x all over h. So in this case, what we get is we get the limit as h goes to 0 of, let's see, so here, what is the function? Well, the function is x to the n, right? So we would have x plus h raised to the n minus x raised to the n all over h. This is where things get a little bit more complicated because we don't really know the power to which we're raising this. We did this in chapter 2 in class where n was equal to 2 and n was equal to 3, and we kind of saw that, well, it seems like anytime we do this we get this type of a pattern to emerge, but of course who's to say that it doesn't work for 4 after working for 2 and 3, right? We have to prove this generally for all n. And so it comes down to actually a piece of mathematical knowledge that helps us expand a binomial anytime we have a variable exponent on that binomial. And that piece of artillery is called the binomial theorem. Many pre-calculus courses will include the theorem in the course, so I'm not going to review it here, but I will tell you that if you want to see justification for the next step, look no further than the binomial theorem. There's a nice Wikipedia page on it. So let's go ahead and try this using the binomial theorem. So it'd be the limit as h goes to 0. When I expand this, the way it works is it's going to be n choose 0 times x to the n h to the 0 plus n choose 1 times x to the n minus 1 h to the 1 plus all the way down till I get to the end of this, which is going to be, let's see, so n choose, these indices go up by 1 until we get to n choose n. So I'll do the last two terms, n minus 1 x to the, what is going to be x to the first, h to the h is matched what's on bottom, so h will be to the n minus 1, and the last one will be n choose n, x to the 0, h to the n. So that whole thing is equal to, from the line above, is equal to just this whole thing by the binomial theorem. Okay, so that whole thing is equal to what's above by the binomial theorem. I hope that makes sense. But it also seems that then we're missing one x to the n right there, and we put that all over h. I mean, right away you see this is a much more complicated argument than the last one we did, right? We're certainly not getting 0 up top. But something, you know, I mean, some things should be sort of popping out at you. In particular, this second term right here seems to be, you know, tied to the result, right? The thing that we were trying to prove here. So in the next line, let's go ahead and simplify a few things out. The first thing to simplify is to think to ourselves, what's n choose 0? So this is, you know, the binomial coefficient, or if you like, these terms come from the nth row of the Pascal's triangle, if you're familiar with that. And anytime we choose 0 things from n, there's only one way to do it, right? Anytime we choose n things from n, there's only one way to do it. And then these coefficients, of course, are you know, much more complicated to calculate. But the idea is that you know, if you're in Pascal's triangle, 1, 3, 3, 1, 1, 4, 6, 4, 1. If you've ever seen this before, these first terms, those are these ones. These last terms are these ones. And the terms in the middle, of course, are these middle terms. And so, you know, if you square out, you know, x plus 1 squared, then these will be the coefficients on x squared 2x plus 1, right? And these will be the coefficients if you do x plus 1 to the third. It'll be x to the third plus 3x squared plus 3x plus 1. So it's a quick way of, you know, sort of programming what happens when we raise something to the nth power. So I guess getting back to what's going on, here we have an x to the n, h to the 0, anything to the 0 is just 1, and n choose 0 is just a 1. So this one and that one are actually the exact same terms. And of course, this is what we saw happen, you know, both in the squared and cubed version of the derivation that we're doing, that the first and last terms cancel. And then what's left inside, of course, everything has an h. So what I'm going to do is what's left inside, I'm going to factor out the h and draw your attention to what's left. We get n choose 1, so that will be just n times x to the n minus 1 plus dot, 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 I guess down to n choose n minus 1. We factored out 1h out of everything here, so the h coefficient is going to go down by 1. So we'll have x to the first, h to the n minus 2, and then we'll have, let's see, n choose plus n choose n, x to the 0, h to the n minus 1. We have that all over h. So the h's will cancel, and we'll be left with just this term up here. And every single term up until this last one will have an h in it. So when I take their limits, we'll have the limit as h goes to 0 of, sorry, made a little mistake there. N x to the n minus 1 plus, I guess it'll be, what'll be n, that was n choose 1, this will be n choose 2, x to the n minus 2, instead of h to the second, it would be h to the first, because I canceled 1h down to n over n, or not over, but n choose n minus 1. X to the first, h to the n minus 2, plus n choose n, x to the 0, h to the n minus 1. So we have this, like, you know, expandable polynomial. It just depends on what the degree of n is. But what should be apparent to you when you sort of look across this is that every term to the right of the first term has some power of h in it, right? There's an h here, h to the first, and then those powers of h will grow until they get the largest term here on the end, which will be h to the n minus 1. So anytime I see an h and I'm letting h go to 0, then what I can say is basically that all of these guys are going to 0. So everything here, including the ones that are in between, are all going to 0. And since there is no h in here, right, I can go ahead and think of this like a constant, pull it out in front of the limit, and take the limit as h goes to 0 of 1, which means that we have just proven that x is, the value of the limit is n times x to the n minus 1, which is what we sought to prove. I know it's a complicated argument, and even worse is that it only works for positive integers. The argument does. It doesn't really satisfy our curiosity for n a real number. But I guess we'll have to wait till later to validate that, because we need some other differentiation machinery on board before we can get at that larger result. It's kind of interesting to me that such a, I guess, a simple rule, one of the simplest rules in differentiation, the power rule, is actually pretty hard to prove, right? You have to pull on board some pretty big machinery, right? The binomial theorem. You have to argue, with an ellipsis, which means that, it's as infinitely expandable depending on how big an exponent we have. But in the end, it really comes down to that second term in the binomial theorem as the only term that comes through without an h, because it's the only one with h, with an exponent on h equal to 1, which then cancels with the h down below after first and last terms cancel each other out. So that's the idea. Complicated argument for sure, but now we can go ahead and just assume it's true for all n, at least these n's that are positive integers. And again, just impressing on you, there's more to this story coming later. Okay, well, what about this? A little bit easier to prove is that if c is a constant and f is a differentiable function, then the derivative of c times f of x is just c times the derivative of f of x. So in other words, that constants can come out in front of a differentiation argument. Let's see if we can prove that. I'll switch over here again. So I guess let me get my notes just to make sure I know what I'm doing here. Yeah, this one's pretty easy to get at. We think the hypothesis here is that d by dx of c times f of x, right, is just equal to c times d by dx of f of x. Meaning that multiplying a function times a constant, all it's going to do is scale the derivative of that function by the constant. I hope that makes sense. Let's see if we can prove it beyond a shadow of a doubt. D by dx of c times f of x. Well, let's just kind of figure out what happens here. This will be the limit as h goes to 0 of the function. This is the function now evaluated at x plus h, so it'll be c times f of x plus h, right? Minus the function evaluated at x, which is just going to be c times f of x. That all over h, right? So in other words, this is the difference quotient for that particular function. Noticing that there's a c in both terms on top, I can go ahead and factor that out. In fact, I can call this the limit as h goes to 0 of c times f of x plus h minus f of x all over h. And now I know that for limit laws, there's a rule that the constant can come out in front of any limit. So that means that this is c times the limit as h goes to 0 of f of x plus h minus f of x all over h. And I notice that this thing, right, is just the derivative, right, of f of x. So we have c times the derivative of f of x, which is what we sought to prove. So we've definitely proven that beyond a shadow of a doubt. So it's sort of strange, if you've never seen an argument like this, we're really, we don't even care what the function is, right? So this is a very general result. This function could be an exponential function. This function could be a polynomial. This function could be a sine function. But anytime I take a derivative of a constant times that function, I can just pull the constant out in front and take the derivative of the function that remains. So that's a really, I guess, a useful tool because it's really broadly applicable. let's go back to, I guess, here. So it turns out that you can also, if you have two differentiable functions and you're adding or subtracting them, you can apply the derivative to the first function and apply the derivative to the second function and just carry the addition or subtraction outside. So, I mean, one way of saying it is the derivative of a sum is the sum of derivatives, or the derivative of a difference is the difference of the derivatives. Let's go ahead and prove that. Let's see, I want to go back to here. So let's see, our hypothesis is that, let's do the sum, and we'll leave the difference up to a similar technique. So I'll do that. So that's our hypothesis, that the sum can be, I guess, the derivative of a sum of functions is equal to the sum of the derivative of the functions. Here's our proof. So off we go to the races. Let's put the left-hand side up, d by dx. This is a fairly wide argument, so I'm going to actually try to squeeze it in here. D by dx of f of x plus g of x, right? So this will be then the limit as h goes to 0 of both of these evaluated at x plus h, right, on top. So f of x plus h plus g of x plus h. So that's the first term, and we're going to subtract. I'll use curly braces, f of x plus g of x, right, all over h. So what do we have here? Well, we have just the difference quotient, but it's a little bit more complicated because the function itself is the sum of two functions, right? But again, we're just applying the difference quotient. This is just rise over run as h goes to 0. We're trying to get a sense of the slope of the tangent line or the instantaneous rate of change of the sum of the two functions. So now you can kind of see what's going to happen here, right? This piece right here, that's the difference function. That over h is the difference function. The difference quotient for f. This function here over h is the difference quotient for g. So if we can just separate those two things, put a limit in front of both of them, then we've got this result here. So that's what I'm going to do next. So I'm going to say, well, this is the same thing as the limit as h goes to 0 of f of x plus h minus f of x plus g of x plus h minus g of x all over h, right? So knowing what I know about fractions, I could say that this fraction over h plus this fraction over h is equal to, what's written here. So I guess I could rewrite this as the limit as h goes to 0 of f of x plus h minus f of x all over h, plus I'm going to go ahead and distribute the limit to the other piece too, as x goes to 0 of g of x plus h minus g of x all over h. And so this piece I notice being the derivative of f of x. This piece I notice is the derivative of g of x. And so we've shown this to be true. So you kind of can see that what this depends on, well, it depends on one, the fact that you can distribute the limit to two pieces in the argument, which is, we know from limit laws. And it's just a smart rearrangement, basically, of what's on top of the original argument for the difference quotient, right? Which is sort of dictated by where you need to get, right? You need to get f of x and g of x sort of separated. So yeah, you just group them left and right and apply the limit to each of the difference quotients, and you get it to pop out. Again, a very general result, right? Doesn't matter what f and g are. This could be a sine function, that could be an exponential function. But if I know the derivative of each, then all I have to do is apply the differential operator to each part and just join them with a plus. see where we at. I'm back to here, right? All right, we're finally to the examples. I mean, so those are the first four, derivative shortcuts. I mean, by shortcuts, what I mean is that we now no longer have to pull out a difference quotient and deal with limits anymore, because we should be able to sort of get at a certain number of these functions with just shortcuts, and that's what all of Chapter 3 is about. So let's just start out this idea here with example. If we know that f of x is equal to 2x squared plus x minus 15, then what is the derivative of that function? I've got it written down now. Let's go after it. And let's do it nice and slow here, right? So we're going to find f prime of x. That's what we're trying to do here. Okay, so literally what I'm trying to find is f prime of x. So f prime of x is going to be equal to the differential operator of f of x, right? I want to take the differential operator across the function. So I'll take the differential operator and put it across 2x squared plus x minus 15. Oh, my table's sort of squeaky, sorry. Okay, so right away what we notice is that we have a sum of two functions and a difference of two functions. So probably the first thing to do is to use the sum and difference result to take the derivative of just 2x squared plus the derivative of x minus the derivative of 15. So I hope you understand that what I've just applied there is what we just proved, right? This idea that, the derivative of the sum of a function is equal to the sum of the derivatives of each of the functions, and of course that could be a minus too. I've applied it twice, right? I applied it here and then I applied it here. But you can imagine that you could do this in two steps, right? You could say the derivative is the sum of this function and that function, and then this one you could split up into that function and that function in the second step. I just did both of them at once. This is what typically we do when we think in our thoughts. The sum of or difference of functions is the derivative of each one of those parts and pieces. Okay, so let's operate on this one next. I notice that I have a constant multiple, and constant multiples can come out in front according to the second rule we derived, right? So I'll take the constant multiple out in front as a 2 times the derivative, right, of x squared. Then I just have d by dx of x. And here I have the derivative of a constant, and I know that derivatives of constants are always 0, so this will be just minus 0. That was the first rule we proved, right? Okay, so we're almost there. Now we just have to find the derivative of both of these terms, and I would encourage you to think of them both as power functions, because we can use rule 2 now on the power functions. So it would be 2 times this guy's derivative, 2 will come out in front, times x to the 2 minus 1, that's the power rule, plus this one, number 1, will come out in front, 1 times x to the 1 minus 1. So let's just, I'm just doing this slowly, right, because I want to make sure I don't lose anybody, but these both are the power rule, and so what do we get for an answer? We get 2 times 2, that's 4. X to the 2 minus 1, that's just x to the first, so 4x. And then here I get a 1 out in front, right? X to the 0, and this would, anything to the 0, of course, is just 1 itself, so I could kind of think as that one is just a 1. So we get 4x plus 1 as our solution to f prime of x. So f prime of x is equal to 4x plus 1 when f of x is equal to 2x squared plus x minus 15. So this guy is that guy's derivative. You can kind of see this happening, right? The constant goes away as 0. The derivative of x as a power function, well, that's just 1. And the derivative of 2x squared, 4x to the first. So we get this as an answer. I don't know about you, but I kind of like to check it. So let's just go ahead and put it into Desmos, 2x squared plus x minus 15. So I'll put it in as f of x equals 2x squared plus x minus 15. All right, well, yeah, it's got a y-intercept of negative 15, so it sort of looks like that. I don't know, I don't like the y-axis or the x-axis scaling, so I'm going to go from negative 10 to 10 just to get a better picture. Okay, yeah, classic parabola, right? So we can right away plot f prime of x just to see what it looks like, and of course it is linear. It does look like it has positive slope, right? But let's just check. One of the ways you can check this, if I make this into sort of a dotted line, we can put another function in, call it g of x. Can't call it f of x because we already used that. And let's let g of x be what we think algebraically is the function. It's 4x minus, oh, no, sorry, plus 1. And I don't know if you can see this, but what happens when I turn g of x on and off is that it overlays the derivative, which is calculated here, I think, numerically. So indeed, it seems like we've found the derivative of the function. Some things seem to agree with us in our mind. Number one, this function here is decreasing until I get, close to, I guess, close to 0. I don't know exactly where. It looks like it at negative a quarter is where this guy's vertex is located. Yeah, negative quarter is where the vertex is. So in other words, we're decreasing until we get to that x value of negative quarter, and then we're increasing, right? So we're negatively valued derivative, positively valued derivative. The other thing that should make sense to you is that, we talked about this before, but polynomials have this stair-stepping effect when we take their derivatives. A second-degree polynomial will always have a first-degree polynomial as its derivative, meaning that any parabola has a line as its associated derivative function. How'd that feel? First big derivative, right? This means that you should be able to do any polynomial fairly easily, right? Their derivatives are fairly quick and easy to compute. Okay, let's talk about this function. Try a different one. Oops. So let me write it down first. G of z is equal to z plus 3, 2z minus 5. And we're supposed to find the derivative. So we're going to try to find g prime of z. I'll go ahead and switch back over to my, here, right? Yeah. Well, so one of the things that you should have noticed in our list of rules is, we have the product here of two functions, and we have nothing right now in terms of rules we've derived for products, right? What we have is we've got a constant, derivative of constant. We have derivatives of power functions. We have derivatives of sums and differences, right? And that's really it, right? That's everything that we've done, right? Constant, I guess, is the first one we did. Power functions, second one we did. Oh, constant multipliers, I guess we have that, right? We do have multiplication when one of these is a constant, but that one's not a constant, right? And then, of course, we have sums and differences. So right away, when you look at this, what your reaction should be at first is like, I don't know how to find that derivative because we haven't done it yet. And I'm sort of nodding at sort of what's going to come next here. We're going to have to come up with some sort of a product rule for derivatives if we want to handle this in the way that it stands. But you're probably like pulling your hair out like, come on, Roscoe, we know what this thing is. This is just a polynomial. It's another one of these parabolas. You just have to multiply it out first, and then we'll be able to deal with it. So that's exactly what you should probably do. If you go ahead and multiply it out, you get 2z squared for the first term, minus 5z plus 6z minus 15. And let's see, so that means that gz is really 2z squared minus 5 plus 6, so plus z minus 15. And, this was kind of like a sort of a joke. I don't know if you noticed, but it's actually the exact same function we just did, right? So we know this guy's derivative right away from the previous one. G prime of z is just going to be 4z plus 1. This would be by previous example. So I guess what am I trying to teach you here? I'm trying to teach you that you should look critically at the function you're given and ask what tools you have and adjust the function into the form where you can use the tools that you have. So that's what I'm trying to teach you. So anytime you get something in product form in this chapter, you're just going to want to multiply it out until you get it in sum and difference form and then deal with that. Hope that makes sense. Okay, well let's take a look at this one. S of h is equal to negative 12 over the square root of h, right? So what would we do here? And again, you should be asking yourself, well, what I see is a function on top constant, a function on bottom, which is not a constant. So we sort of have this quotient type of a situation. So a lot like above, I have a product here, don't have a product rule, so I need to sort of multiply it out, put it in a different form so that I can use the tools I have. You should be thinking the same thing here. Like if I could write it in some form where I could use the tools for differentiation available to me, then I should be able to find an answer. And so let's start transforming the way we write the function. Let's take the negative 12 and put it out in front. And let's call this 1 over. And instead of square root, I'm going to write that as h to the 1/2. And this will generally be the rule anytime that you're dealing with roots. It's easier to put them into exponential form to take derivatives. So anytime I have 1 over something, I can write this as negative 12 h to the negative 1/2, right? And now this thing is nothing but, a constant times a power function. And I know how to deal with power functions, right? So let's go ahead and attack this one. So s prime of h is going to be d by dh, right? We're taking the derivative with respect to h here of negative 12 h to the negative 1/2. Okay, so the negative 12 can come out in front because that's just a constant multiplier. Negative 12 times d by dh of h to the negative 1/2. And now I just have a power function, right? It doesn't matter that it's negative. You can do power functions for all real number exponents. So what do we get? We'll get negative 12 times, take the negative 1/2 and put it out in front. Take the original exponent and subtract 1 from it, right? So we get negative 1/2 minus 1/2 more. Negative 12 times negative 1/2. So it looks like the answer here is going to be, let's see, 12 divided by 2 is 6. Negative times negative is positive. So we get 6h to the negative 3/2 as our derivative function. I don't know about you, but I wouldn't have guessed that right off the bat. So it's probably worth taking a look to see if this is really the derivative of the function we're after. So let's go to Desmos again. Instead of 2x squared, we're going to put in what? Negative 12, that whole thing, divided by square root of h. So sqrt will do it. And instead of h, I'm going to use an x. Okay, so there is the function in red and its derivative in blue. One of the things you should notice is that this one has a restricted domain, and of course that makes sense because we can't have negatives in square roots. Those are imaginary numbers. We're talking about real number calculus in this course, so thank goodness we don't have to talk about complex numbers yet. But that's the derivative, and let's just check to see if we have it. So we would be checking to see if 6 times x raised to the negative 3/2, right? Negative 3 divided by 2. Drum roll, please. Boom. Yeah, looks like we got it. So again, some nice ways you can use technology to check your answers, especially when you're in uncertain terrain, which is probably where you're going to be a lot this chapter. So, all right, I want to do 2 dreamy problems that I just find really interesting to end on here. I know let's see, I'm at 40 minutes. So yeah, I've got about 10 minutes left in the lecture here. I just can't help myself when we get close to sort of things that we we're familiar with, and that this new mathematics gives us new eyes to see them more deeply. You're certainly at that point now where you're going to start seeing the inner workings of some objects that you've been very familiar with across your math education. So let's start with one we're all super familiar with. If a, b, and c are constants, differentiate the function. Okay, so what are we doing here? We're sort of thinking of like all polynomials, right? Second degree polynomials. I mean, this would be the general form for the quadratic, right? And we know that we have this thing that solves these. So what information can we glean by doing a little calculus on this? Let's just see, huh? All right, so I need to get back to my... So let's see, what do we want to know? We want to let f of x be equal to ax squared plus bx plus c, right? And we're after f prime of x, which is going to be the differential operator applied, right, to the function ax squared plus bx plus c. Okay, well, we know the differential operator respects addition, so we can just take the sum of d by dx of ax squared plus d by dx of bx plus d by dx of c. That's just the rule for sums and differences of functions. I can see that a, b, and c are constants, right? A, b, and c are constants. Okay. Sometimes we call these things parameters because, yeah, they're constants, but we're not specifying them. But I can see that the constant here can come out in front, right? And then the derivative of a constant here, well, that's just 0, right? So what we're going to get is d by dx. Oh, I messed that up a little bit. What should come first? A, right? Take the a out in front. A times d by dx of x squared plus b times d by dx of x, right? Okay, so now we can take the derivative of x squared, and what do we get? We get a times 2 comes out in front, we get x raised to the 2 minus 1, right? Plus b times d by dx, we can think of this like a power function with exponent 1, so we get 1 out in front times x to the 1 minus 1. So this is just x to the 0, that's just a 1. So we end up with just 2ax, right, plus b, right? So that line, 2ax plus b, is the derivative to any one of these quadratic functions, right? So let's just go and play around with this in Desmos to see what we have discovered. So here's what we're going to do. We're going to put in the function ax squared plus bx plus c, right? We're going to get a slider for all of these. So in other words, a is sort of this thing that adjusts the parabolas, I guess stretches it vertically, or b is kind of interesting. It sort of pivots the parabola around its y-intercept. That's the way I think of it anyways. And of course, c is just the y-intercept of the parabola. We can move the whole parabola up and down. And there's some really neat things to think about here. When I adjust c, well, first of all, let's just verify that we have the right answer. Is that dotted line, the derivative of the function, indeed 2ax plus b? Drum roll, please. Boom. Of course it is. We did it right. So that's definitely the derivative. But here's some things that are kind of fun to think about. You know, why does adjusting c not change the value of the derivative? You had a couple questions like this in the conceptual chapter, chapter 2, but shifting a function vertically doesn't change the equation of its derivative, and that should make sense to you, right? Because all you're doing is you're shifting the function vertically, but you're not changing the locations of all the slopes. In other words, the slope here is the same if I move it up or down, right? as the slope, right here. So in other words, the slope at any one given value of x doesn't change by shifting the function up or down. It'll change by shifting the function left or right, or by dilating it, right? Which is what I guess the b and c do. Even more interesting is asking the question of like, well, how, what does this thing have to do, right? Well, the function itself, right? I guess one of the things we've always been after with quadratics is their vertex. And, we can use the derivative now to get at where the vertex is located, right? And so the vertex is going to be located where the derivative function transitions from negative to positive, right? That's where we come down, change, and then go up, right? So at that location right there is where we should be able to find sort of a general form for the vertex, right? A general x value for the vertex. So let's go after that really quick just to see what happens here. To find the x value of vertex, set f prime of x equal to 0, right? Find the spot, right, where the slope of the function is equal to 0. This is the slope of the function, so where is 2ax plus b equal to 0? Well, I'm going to solve for x here. I'll get 2ax equals negative b, and I'll get x equal to negative b over 2a, right? So this value of x is where that function is. So the vertex is located at negative b over 2a, comma, f of negative b over 2a, right? So in other words, the vertex is found at this value of x plus the value of the function at that value of x. Let's go ahead and plug it in and see if it really works. So in Desmos, I can just type in ordered pairs as coordinates. So negative b divided by 2a, and comma, f of negative b divided by 2a. And man, there it is, right? You see it on the graph. And what's really fascinating about this to me is that that should basically dynamically follow the vertex no matter where I put a, b, or c, right? In other words, the theory basically is predicted universally using the derivative. Another really interesting thing to think about is that maybe you've recognized that value right there as the first part of the quadratic formula. And remember, what the quadratic formula does is it tells you the zeros of any quadratic function. So in other words, this quadratic function right here has zeros right here and here, right? Right here and here. So if we plot, this might help you see it, x equals negative b divided by 2a, then that's the, I guess that line, that green line that we see there, I'll dot it, is the axis of symmetry of a quadratic function. Any quadratic function is going to have that as its axis of symmetry. I can sort of move this and the axis of symmetry will change with it, right? And if I turn off, I'm going to turn off the derivative here really quick. So if you kind of think about it, the quadratic function adds and subtracts a quantity to that negative b over 2a. So if I want to find that 0 and this 0, what I do is I start here and I add or subtract the same value. So the quadratic formula can be understood as sort of an adding and subtracting from that center line, that green center line, right, of the function. So to me, I don't know, I just think it's so incredible that, we can turn to, calculus to get a new sense of like, okay, where's, the derivative equal to 0? That's going to tell me where the vertex's x value is every time, right? So now you have this function negative b over 2a given, the general form of a quadratic that can tell you where the vertex is found. It can also give you some insight into, I guess, why that term negative b over 2a is the first part of the quadratic formula, which solves for zeros. I don't know. I just think it's absolutely stunning. I hope that you're as excited as I am. Let's do one more that I find equally stunning. Given that the area of a circle is pi r squared, find the derivative with respect to radius. Interpret the meaning and what does it mean geometrically. So let's go ahead and talk about that next. So let's see. So we have that let me just get here. The area as a function of r is just pi r squared. And what we want to know is what is a prime of r. In other words, what's the derivative of area with respect to r? And this is a simple power function, so we should be able to get its derivative. So a prime of r is going to be equal to d by dr of pi r squared. So we're taking the derivative with respect to r here. This is a constant, right? So it can come out in front. Pi comes out in front. We get d by dr of r squared. This is a power rule, so 2 comes out in front. 2 comes out in front. We lower the exponent by 1. So what we end up with is pi times 2r, which is the same thing as 2 pi r, right? And I mean, it's no coincidence here, it can't be, right, that the derivative of the area function is the circumference function. So the answer, I guess, to question 2 is this is the circumference with respect to r, right? Question mark, right? Super strange, right? It seems to like be a very surprising idea, or I guess result, and let's see if we can get a sense of what's going on, right? I'm going to draw a quick circle here and try to argue what's going on here for you. Here's your circle. Okay, it has a center and it has a radius, right? And the question is how fast is the area changing with respect to r for a given radius, right? And what it says is that the area is changing about by the circumference. So one way you can kind of think of it is that if I change the radius just a little tiny bit, right? If I change the radius a little tiny bit, we'll call that little bit delta r, okay? And I've shown it in sort of expanded view. It would be much smaller, I guess, if we kind of think of infinitesimals, right? If I do that, then what I've done is I've added this portion, right, to the area, right? So if I take the radius and I expand it just a little bit, how fast is the area changing? And I think you can see that kind of what's going on here. If I sort of snip this or think of this unrolled, right, that what I've added is a bunch of new area that's approximately equal to, the circumference of the circle, right? So in other words, the amount of area that you add, right, for any one given radius is approximately equal, right, to the circumference itself. So in other words, you can kind of think of like snipping this and unrolling it, right? And you get some long skinny piece here, right? Where this is 2 pi r and this is delta r, right? So you're getting just a little piece, right, of the circumference. I hope that makes you excited. I mean, I think that's just absolutely stunning that, the derivative of the area is the circumference, and that we can kind of see geometrically why that happens. If we slightly change the radius, then what we're doing is just really adding a piece of circumference to the area. All right, well, that's really it for today. I'll be back tomorrow for a review before the exam over Chapter 2. I will say this, that this particular chapter is really helpful to check your answers on the exam that's coming up on Friday. But know that we will certainly ask you to use the limit of a difference quotient to calculate a derivative. So please don't jump the gun. If you're asked to use the difference quotient, use it. But I would certainly tell you that you can use the tools in this chapter to check things or to know exactly what it is you're supposed to be getting, especially if we ask you to take the derivative of a simple polynomial on the exam, which is probably the type of question you can expect, taking the derivative of a simple polynomial using the difference quotient. Something similar to, I guess, question 3 on quiz 3. Okay, you guys, I look forward to seeing you all tomorrow, and wishing you well until that time.